Hello and welcome to Spur Economics. Today, we're diving into an essential concept, autocorrelation. We'll cover what it means, its causes, and consequences. Please like, share, and subscribe if you like our content. Visit the Spur Economics website for more knowledge on econometrics, link is in the description. In the context of econometric models, autocorrelation is a situation where the error terms in the model are correlated or dependent on each other. Error in the given period, therefore, is determined by errors in the previous periods. It is a common problem faced by economists because of the nature of time series data, where successive values of variables and error terms affect current period values. One of the assumptions of OLS states that there should be no autocorrelation in the model. It is also referred to as serial independence. Serial independence means that the error term in any given period is independent of error terms of other periods. That is, the error terms do not affect each other. In general, autocorrelation, also sometimes called serial correlation, refers to the correlation of a time series with its own past values. Essentially, it's the relationship between observations of a variable over different points in time. For instance, if we have a time series of GDP growth rates, autocorrelation would measure how current GDP growth rates relate to past rates. If high growth rates tend to follow high growth rates and low growth rates follow low growth rates, we have positive autocorrelation. Conversely, if high growth rates follow low growth rates and vice versa, we have negative autocorrelation in the GDP growth rates variable. The terms autocorrelation and serial correlation are usually used synonymously. But there is a theoretical distinction between the two. Autocorrelation occurs when the current value of a variable is dependent on its own lagged values. On the other hand, serial correlation is a situation where the current value of a variable is dependent on the lagged values of another variable. Omission of important independent variable. If an important independent variable is not included in the model, then its effects are captured in the error term. As a result, errors will become dependent on each other if the excluded variable is autocorrelated. Time series variables tend to be autocorrelated due to their inherent nature. For example, income in the current period is generally related to the previous period's income. If the income variable is excluded from the consumption function, the model may end up being affected by autocorrelation. This is because the excluded income variable is most likely autocorrelated and will be captured by the error terms. Nature of problem. In some cases, error terms are autocorrelated due to the nature of economic phenomenon. Let us consider an example of agricultural production and droughts. Drought, here, is a random factor that might end up causing autocorrelation. This is because the drought will affect production not only in the current period but also in the next periods. Hence, autocorrelation may exist because certain random factors have their effects over a longer period or across more than one time periods. Misspecification of functional form. A wrong functional form of the model may also cause autocorrelation. For example, if the true relationship between variables is cyclical, but the model uses a linear functional form. In such a case, the error terms might become correlated as the cyclical effects are not addressed by the explanatory variables. Non-stationarity. A time series is stationary if its features, such as mean and variance, are constant over a given period of time. If the time series variables in a model are non-stationary, then the error term may also be non-stationary. As a result, the error term might be autocorrelated with varying characteristics, such as mean, variance, autocovariance, over time. Inefficient estimates. While ordinary least squares or OLS estimates remain unbiased in the presence of autocorrelation, they are no longer efficient. This means the estimates do not have the smallest possible variance, making them less reliable. The true variance of parameters becomes large in the presence of autocorrelation, while the estimated variance of coefficients is underestimated. The estimated variance of coefficients is smaller than their true variance. Underestimation of residual variance. The variance of the error term is underestimated if the errors are autocorrelated. If the autocorrelation is positive, then this problem can become even more serious. Tests of significance. Usual tests of significance like standard errors, t-test and f-test will give misleading results and are no longer reliable because the variance of coefficients is underestimated. These tests cannot be used to determine the statistical significance of coefficients. The estimated standard errors will be smaller because of underestimated variance, thereby affecting t-values as well. Predictions. In autocorrelation, the predictions made by the OLS model will be inefficient. This means that the predictions will have a larger variance as compared to predictions from other models like GLS. Autocorrelation can be detected using several methods such as the Durbin-Watson test, Birch-Godfrey LM test, ACF and PACF plots. To address autocorrelation, econometricians often use techniques like the generalized least squares or Newey-West standard errors, which adjust for autocorrelation and provide more reliable estimates. To learn more about the detection and solutions to autocorrelation, you can take a look at the links in the description. If you found this video helpful, don't forget to like, share, and subscribe to our channel for more in-depth discussions on econometric topics. Leave your questions and comments below. See you next time.